It's really just trying to understand the different types of error characteristics, whether it be random and systematic, and how it relates to a quantity of interest. And the quantity of interest really can be any sort of a fundamental science parameter that is trying to be estimated or measured. And sea surface temperature, I think, was a really great example that was called out quite a bit in the paper. But the paper itself really focuses on 4 perspectives from discovery. Fundamentally, it's mathematical, and the mathematical is really where we get down to the actual constructed definitions for uncertainty and all the different components that go along with it. And then programmatic, you might think that's dealing with the computational aspect, but it's actually dealing more with the more of the governance of it from a perhaps you might say a legal perspective, or maybe even a program support perspective, whether it's a NASA program or a NOAA program, or whether it's a UN initiative or something abroad. So we try to cover some of those perspectives there. And then in the observational realm, the paper itself is primarily focusing on observational data. There really isn't much focus on modeling or assimilation. And that's really part of the purpose of this session today is we're really trying to dive into more of that perspective that we really didn't get an opportunity to cover in this paper, and as well as leading up to the paper. And then lastly, the user perspective, dealing with the various ways in which users might interpret and try to understand uncertainty information and make use of it. So the paper really was just trying to identify commonalities and differences once all these perspectives were put down on paper. And I think one of the really interesting things was all of the co-authors represented various aspects of earth science. Some oceanography, many people were representing remote sensing, I would say. A few were representing data science and statistics and metrology. We didn't have many on in situ, although we had 1 or 2 that represented that perspective. And then the in situ area is another thing that we wanted to try to explore further on as a follow-on to this white paper. And some fundamental researchers were part of it as well. So here are some of the key takeaways. So really, there's quite a bit of diversity in the way that uncertainty is quantified and characterized, how it's disseminated, how it's consumed, various methods of interpretation. I think the biggest commonality here is there's a shared interest, a collective interest in the need to have uncertainty for pretty much any type of earth science data set. That was unanimously agreed upon, as well as there needs to be a commonality and approach to how it's estimated, how it's interpreted, and potentially even how it's packaged and disseminated. So while the paper doesn't really go into making concrete recommendations, I kind of think of it as providing that foundation where we can now go ahead and do that. So we have, as I mentioned, statistical techniques based upon UQ and UC, but we also acknowledge that there is also knowledge-based techniques, which are not necessarily computational, but a little bit more of a knowledge-based technique. We didn't really go into depth on what that looks like, but just to call it out as another way of doing it. The other thing is that UQ-UC is ubiquitously recognized as a fundamental step, taking us to providing vital information that helps characterize, as I mentioned earlier, the science quality of the earth science data that is being collected, evaluated, assimilated, and ultimately applied from the end user perspective. And ultimately, the UQ-UC information depends primarily on effective communication and dissemination of that information, and that really helps drive the effective utilization of that. We discovered that very few data users have a proper understanding of the probabilistic framework that establishes correct interpretation of the data. What I mean by that is generally people just want to see error bars, but they don't necessarily care to know the probabilistic makeup of what those error bars represent in kind of a PDF space, probability distribution function space. And so that's something that we call out as a potential pitfall that users might fall into when they try interpreting error bars. Programmatically, there seems to be a growing trend, I would say, in kind of requesting or even requiring the presence of uncertainty information. And we see that particularly, for example, in the world of CEOS and in Europe with the essential climate variable or ECV framework, where they're requesting these things for whether it be climate data records or Earth system data records. And in the suborbital and in situ world, I would say one of the challenges here is that there's a lot of these smaller niche communities, and they kind of have their own very specific priorities and concerns for UQ-UC. and so it's really just one of those things that we really need to try to penetrate a little bit better. And this is just going into some of the authorship acknowledgements here. Some of these names might look familiar to you. I will call out Jonathan Hobbs was the champion. We designated champions for the fork perspective. So he was the champion of the mathematical section from JPL. And I'll call out, let's see, who else do we have here? We have others that are on the first page that are not on this list. So we have Rama, who is the champion of the programmatic section. We had Bob Downs championing the user perspective section. And we had Justin Goldstein, who's listed here, who at the time was working for NOAA. Now he's moved on, I believe, with DoD. But he was championing at the time the observational perspective. These are all the affiliations of the co-authors, and this was again at the time of the publication of the paper. Okay, so we had a winter ESIP meeting session to continue these discussions, and we wanted to, as I mentioned, explore some of the lesser penetrated subjects regarding suborbital and in situ. So we had two presentations. The first was provided by Professor Fred Bingham from University of North Carolina, Wilmington, and he's also the data manager for the submesoscale ocean dynamics experiment, also known as SMODE, which is a NASA Earth Ventures class suborbital mission, or EVS mission. The campaign is really primarily meant to observe ocean dynamics and vertical fluxes for climate and biological parameters in the kilometer scale within ocean eddies. And so it's kind of a proof of concept, but more so from combining it in situ and 4 different types of aircraft. And the observations are really intended to help establish ground truth for space-based platforms for UQ estimation. And one of the things that was called out from the presentation is that space-time representation error is perhaps the biggest issue with in situ observation. We had another presentation. This is by Dr. Mikhail Kusela, who's a data scientist from Carnegie Mellon University. And he looked specifically at researching uncertainty quantification techniques for the Argo float data using spatiotemporal mapping products. And so at the time he presented this, there was 3,856 Argo floats circulating in the ocean. I don't know if that's still the number today, but at the time he presented this, that was the number. And so the other primary point here was that the legacy products he was working with either did not provide UQ information natively, or they used very statistically ad hoc techniques. And so there was a real lack of consistency for any UQ information that was out there. There was a pretty good lack of consistency. So really, he was just trying to bring consistency to this. I think that's one of the paramount goals here that he was trying to do. And I believe he's still working on this. It's an ongoing effort, but there's a lot of things that came out of this. So one is, despite the large number of floats, the data is quite sparse. And so that relegated the downstream products to interpolated products. And so the UQ, the interpolated maps, really depends on the covariance length scales. And this is essentially varying from one location to another. He also discovered that obtaining the realistic UQ requires, you got to make sure you handle properly the length scales, and also take into account the non-Gaussianity of the data. Most of the data that I would say is true in the ocean dynamics world is very non-Gaussian, and so that's something that is commonly not considered. Most uncertainty quantification, they assume Gaussianness of the data. And so one of the things I like about what Mikhail did was he took that into account. More traditional UQ tends to focus on communicating point-wise uncertainty. And then the last thing that I call out here as a key point is, and this is a result of this spatial temporal inhomogeneity of the Argo data, is that covariances here may provide more meaningful information than just the point-wise uncertainty that would help understand uncertainty in a space-time context. So these are some of the actions that we're going to do beyond the white paper. So we're going to draft a part 2 paper, and I'm hoping that from the part 1 and part 2 sessions today, we can come out of that with enough information and enough of a groundswell of support to continue this into drafting an actual part 2 paper. And where we'll talk about today more is the perspectives of, as I mentioned, modeling and data assimilation, perhaps even some additional examples on suborbital and in situ. But there's many more opportunities that exist as well downstream, such as how it's encoded in data files, whether you're using object store encoding or whether you're doing API-based filtering extraction, etc. So we called out in the white paper a lot of opportunities that exist downstream. In light of those ancillary opportunities, I want to call out on July 22nd, which is exactly 1 week from today, we have another ESIP session on this NetCDF UQ proposal, which deals with the actual encoding of the uncertainty information in the NetCDF files. So I wanted folks to be mindful that we have a related session there next week. And going into today's agenda, so I just introduced the topic, talked about recent efforts, and we have our next presentation by Anish, followed by Patrick, and then we'll wrap up with a panel discussion. I will want to point out that Anish does have a hard deadline. He has to leave right at 2:30, so I'll try to transition really quickly to him. And our panel discussion will feature myself and Patrick before we wrap up and take a break. So with that, I will stop sharing. And if we can maybe have Anish share his screen.
Yeah. Can you see my screen now?
Yes.
Okay. Great. Thanks, David, for the introduction. Some of the things I'll talk about will also overlap with what David just talked about. Let's try moving this. Okay. Yeah. So yeah, I'll be talking about about forecasting or prediction systems and how uncertainty is currently represented in these prediction systems, both on the weather timescale, but also in terms of climate, so longer timescale, going from timescale of months to decades. What are the types of uncertainty and how uncertainty is represented in these systems, and why it's important to represent uncertainty in terms of the use of information from these models for stakeholders. And then second half of my talk will be more on the observational side, on what are the different sources of uncertainty in situ observations. And the example I'll give will be from Argo array that David just mentioned, and some work from Kusla and others. My collaborators in this work are Tim Palmer, Antje Weisheimer, who are at the University of Oxford, Peter Bechtold and Frederick Wittart, who are at ECMWF, the European Weather Forecasting Center, and Donata Giglio, who's a faculty here at CU Boulder. So what's the motivation of representing uncertainty in our system? So this figure, a plot is from the WMO, the World Meteorological Organization. What's plotted on the x-axis here is the application for different information at different timescales of prediction of the Earth system. And then the y-axis is the kind of information we get from predicting the Earth system at those timescales. So can you see my mouse too?
It's difficult to see.
Oh, okay.
I see it okay.
Okay, yeah, I'll try not to use it a lot. But so for instance, at timescales of minutes to hours, the information we need is mainly for warnings, alerts, saving lives, saving property. For instance, if there's a hurricane coming in and making landfall, evacuating people out and trying and saving property. So that's information that's given out as warnings and alerts from forecasting centers. As we go out further in time, out to days and weeks, which is the traditional weather forecasting time scale, out to 1 to 5 day time scale. Those are called forecasts. And they are essentially an initial condition problem, as it's called in the weather forecasting community, where most of the uncertainty at these time scales and most of the signal also at these time scales comes from accurate representation of the initial conditions of the model. Then as we go out further into months and seasons and years, the kind of information that's given out at those timescales are more known as assessments or guidance or outlooks. They come with larger uncertainty, and they are not necessarily a condition of a product of uncertainty in initial conditions, but they're also forced by boundary conditions, such as how's the Earth forcing changing, how's the oceans, deep ocean changing. So all of that can contribute to both the signal and the uncertainty on these timescales. And then out to decades and centuries, which is the climate change problem. At those timescales, we do have uncertainty. And the signal at those timescales is a function of the external forcing that we add to the Earth system. So for instance, anthropogenic forcing from CO2 or other greenhouse gases. In addition to like solar variability in solar forcing that can add internal variability in the system. So all these time scales, we have different information, but one thing that is really important on all these time scales also representing how uncertain this information is. And that is key for the use of this information for applications from saving lives to hydro power or managing water resources and reservoirs, out to planning city and nationwide infrastructure. So having that uncertainty is important. How do we get an accurate representation of uncertainty? That's what I'll be discussing in the rest of my talk. So I'll be talking about how uncertainty is modeled in forecasting systems and the impact of stochastic parameterization, which is a way to represent uncertainty in the system, both on the mean of the model and also variability. And I'll describe it briefly in my talk. And then the second half, I'll talk about observation uncertainty, and one slide on uncertainty in data assimilation, which is largely what Patrick will give a very good presentation on that after mine. So what are the sources of uncertainty in forecasting systems? One type of uncertainty is the initial condition uncertainty. And a lot of you might be familiar with this in terms of what's commonly known in literature as butterfly effect. Small changes in initial conditions can lead to large changes in solution at a longer lead time. So representing that uncertainty in our initial conditions of the model is key. The second kind of uncertainty is known as model uncertainty. How accurate is our model? And if it's not accurate, how do we represent uncertainty in these model physics, for instance? And this is just a cartoon on the right-hand side showing all the different complex physics that is represented in the Earth system model. And a lot of the physics, the way they're modeled, they do have associated uncertainty with them. And representing that uncertainty in some way in the forecasting system is key to get to propagate that uncertainty in time. So at the European Center, which is ECMWF, the European Weather Forecasting Center, one of the leading centers in terms of weather forecasting in the world, they represent both these types of uncertainty in their system. The initial condition uncertainty is represented using what's known as singular vector perturbations. Those are perturbing the largest error-growing modes in the system. And another method that's used for representing initial condition uncertainty is an ensemble data assimilation perturbation, where they have multiple representation of their system through the data assimilation framework. And that covariance or variance across the ensemble is used to represent initial condition uncertainty. The model uncertainty is represented through what's known as stochastic parameterization. So that's adding a random function, a random noise function to the model that perturbs the model in a way that represents the uncertainty in our model solution accurately. There's a lot of literature on this over the last decade and a half or 2 decades. This is relatively a new concept. It's been tested in operational weather models only over the last decade, and it's shown really good results. And that's being studied in some detail now, both in the European community and the US NOAA community. So the way stochastic parameterization is represented in the forecasting system, and I don't have time to go into the details of this, but what's done is they take all the physics tendencies. So tendencies in a climate model is essentially at every time step of the climate model, the solution that you get is the difference between this time step and the previous time step. So if you were, for instance, if the model is stepping the atmospheric circulation forward every 10 minutes, the difference between 2 10-minute intervals, that's known as the tendency of different variables. So for instance, what's the wind tendency? What's the difference in the wind in 10 minutes? The temperature tendency, humidity tendency. So these tendencies are the solution of the model equations, and we know that they're uncertain. So what we do is to add a multiplicative noise term. So we do 1 plus a random noise term times the solution. And the characteristic of this random noise term, which is the stochastic term in the system, for instance, the variance of the noise term, the spatial and temporal decorrelation, that is designed to represent how uncertain the model solution is over a long time period. Another type of representation of uncertainty is to represent what physics processes are not being included in the equation. So for instance, there's this phenomena called kinetic energy backscatter, where energy from small scale, so for instance, energy from the gusts, wind gusts that we can see outside our window can be transferred from these small scales to large global scale winds. And that's not represented in our models currently. So we can represent those processes in terms of a stochastic process within the model with some uncertainty associated with them. So what's the benefit of having this uncertainty represented in the model? So here what's plotted on the x-axis is the forecast of weather forecast from the European model, averaged over 20 different forecasts. And the y-axis is the root mean square error of this forecast. So the lines with the cross symbols are showing what's the error in the 850 millibar temperature. So that's the temperature about a kilometer or 2 in the atmosphere from the surface. What's the error in that temperature as a function of lead time of the forecast? So if we look at, for instance, a 4-day forecast of temperature, the error in this solution can be up to 1 degree C. And what's plotted in these straight lines without the symbols is the ensemble spread. So this is a probabilistic forecast. And the ideal forecast should be where these 2 lines overlay, that the uncertainty in your ensemble should equal the error in your forecast. If the uncertainty is smaller, which is true in this case, then the ensemble is known as under-disperser. And here we see that the root mean square error is larger than the ensemble spread. But when we add the stochastic physics, which is the blue and the red line, the difference between the error and the uncertainty and the ensemble spread becomes lesser, which means that it improves the ensemble spread and also decreases the root mean square error. So it's improving the actual physical field and improving the uncertainty in the forecast. So this has been seen over the last decade that this is a really big benefit of stochastic parameterization in weather forecasting systems. Something that's more recently studied is how do these stochastic parameterizations or uncertainty help improve the mean climate of the model. So probably most of you know that climate models do have errors and biases in them. This is an example of precipitation. So the left top panel is the observed precipitation global mean value over a 20-30 year period. And the blue colors here indicate larger amount of precipitation, largely in the tropics, and there are known physical reasons for why this is true. The bottom two panels are showing what's the difference between the model, the weather forecasting model's mean climate compared to the observation. On the left-hand side is when we don't have stochastic parameterization, and the right-hand side is when we have stochastic parameterization. Both of these models show an error or a bias where the model tends to precipitate too much in the tropics, the blue and the green color. But the top right panel is showing us what's the difference when we add stochastic physics. So this is the stochastic physics off minus on case. And here what we see is that the stochastic physics off has more precipitation than the stochastic physics on, which means that having this uncertainty and stochastic perturbations within the model actually reduces the error in the mean climate of the model. So in the interest of time, I'll skip this section, which is looking at another phenomena, the Madden-Julian Oscillation in the tropics. And we see an improvement in the representation of this phenomena as well in the climate model, that it has a big impact globally, and improving that modeling of the MJO using stochastic parameterization is really valuable. So next, I'll take about 2 minutes to go through sources of uncertainty in situ observations. Example is from Argo, which is a robotic float deployed globally around all ocean basins. It's a float that goes up and down in the ocean over a 10-day period. And there are products which are derived from these observations of the ocean. One product is the global ocean heat content. And the reason why global ocean heat content is important is about 93% of the excess energy that we are storing in the Earth system, which is because of the greenhouse gases trapping this energy, 93% of that goes into the ocean. And being able to track that accurately is highly important to understand how our climate is changing and how the climate systems, different reservoirs of energy changes. So the sources of uncertainty into a product like this can be, one, due to the raw quality control of the observation. So how are the Argo observations that are collected from the ocean, how are they quality controlled? Are we checking if there are outliers, if there are errors in some observations due to some reasons of the observing system? That can affect the uncertainty. Another source of uncertainty is bias correction. For instance, some observations like XBT data from ships have a known bias, and being able to correct that accurately is another source of uncertainty. A third reason for uncertainty in observing systems, specifically towards derived products like heat content, is the spatiotemporal data sampling. Different observing systems in the left panel here is showing how the observing system density changed over the last century. And starting in 2000 to 2004 is when the Argo program started. And that's when we have a huge jump in the number of observing systems, both spatially and temporally. But given this wide range of spatiotemporal distribution of data, that adds another additional uncertainty in these derived products over the last century. The fourth reason for uncertainty is the choice of a baseline climatology. So how do we fit a trend in the data? How do we fit a seasonal cycle and the mean climate? And this is, again, work led by Mikhail Kusela, Donata Giglio, Mondal and Stein, which is in prep. And some of this, David did mention that Mikhail gave a good presentation on this to the ECIP group. So that's another source of uncertainty in the data. And then a fifth and sixth source of uncertainty is how do we map this data? What methods do we use, especially if it's Gaussian or non-Gaussian? How do we objectively map this data, and how do the errors from that mapping translate to products like this? And then a spatiotemporal correlation of these measurements and how that correlation is modeled can lead to improved uncertainty estimation on these products. And all of this uncertainty, just one plot on data assimilation. So the data assimilation machinery ingests observations and model, and then comes up with a better updated model state. There is uncertainty in observations, as I just mentioned, and there are sources of uncertainty in the model state as well. Both this, if represented accurately, can be translated through this assimilation system into an updated model state, which can then be used to initialize the forecast and get a better forecast and a model state at the next time step. So with that, I'll end with this quote from Ed Lorenz, who quoted in 1975. This is Ed Lorenz, who's famous for the chaos theory and a world famous meteorologist. He said, "I believe that the ultimate climate models will be stochastic, that random numbers will appear somewhere in the time derivatives." Thanks, David. I think I went over a few minutes. I'm sorry about that.
That's okay, Anish. Actually, I went over a few minutes myself, so thank you. I know you have to run, so I appreciate the thought-provoking information, and we'll look forward to having you when you're able to join us in the next part 2 session.
Okay, great.
All right,
Let's
thank you, Anish.
Sharing. Yeah, thanks.
And yeah, so our next speaker is Patrick Heimbach, representing the University of Texas at Austin. And so, Patrick, whenever you get a moment, you can start sharing.
Yeah, thank you. Thanks everyone for for joining this session and for inviting me to talk. Nice to follow on the nice talk by Anish on uncertainty quantification in the context of ocean data assimilation. The first point that I'd like to make is actually that, oops, let's see.
Oh, muted. You are muted. Can't hear you.
Okay, sorry. That should be better now. Yeah, so oceanography is in some ways actually still remains a sparse data problem or sparse data science. Why do I say this? Here, what we see here, these figures here, the Northern Hemisphere, Southern Hemisphere, we see the global coverage in ocean observations from the 1950s to 2010 as a function of depth. We'll see that until the early 2000s, we are barely, or even below the 10% coverage in terms of ocean observations. This only improves at the mid-2000s, as Anish pointed out, is then when we start to have the Argo float array program that allows us to profile up down to 2,000 meter depth. That improves the situation somewhat. It's still, we are at the 40% level, and we still remain sort of data sparse below the 2,000 meter level. But keep in mind that the ocean's average depth is 4 kilometers. And also, if we look at the distribution of observations as a function of latitude, which is shown here in the right panel, we see that there is a mismatch between large coverage in terms of percentage and coverage and the percentage of ocean volume as a function of latitude. So, so this is from a review paper by Abraham et al. 2013. Just I'd like to point out, so something is not working here with my forward, but let's do this then. The ocean is a noisy place. You should hopefully see this animation here. This is an animation from an Arctic Ocean simulation at eddy permitting scales. What we see here is the flow-in of subtropical origin Atlantic water below the surface. So this is subsurface somewhere at 300 meter depth levels. And we see the circulation has some very organized structure, but on top of that, the fluid is certainly a very turbulent one, so a very noisy one. And we need to take into account the observational sampling whenever we talk about or whenever we consider ocean observations. So how do we go about this? So this problem has been sort of thought about already in the 1980s. This is a cartoon drawn by Carl Wunsch on the occasion of Walter Monk's 65th birthday. At the time, there was the prospect of getting satellite data available in the 1990s. The question of how to use these data with the other potential, the measurement technique that was sort of dreamed up at the time, which was acoustic thermometry to measure ocean heat content, and combining this with observations, available observations through in situ measurements that have been available. The question is, this is a very eclectic observing system, and how to make sense of all of these observations in a joint manner. And the idea is that a ocean model, a three-dimensional ocean general circulation model, should serve as the dynamical interpolator. And this goal of providing estimates of the time evolving ocean state that are consistent within the error bars, and so this is important, with all available observations and with known physics and dynamics, is what the project for estimating the circulation and climate of the ocean has set out to do. It's called ECHO. It's been around since the early 2000s. And the sort of what ECHO is doing today, it basically uses this range of observing platforms, satellites here, satellite gravimetry, altimetry from the Topics Poseidon JSON series, passive microwave radiometry to measure SST, now Aquarius and SMOS measuring sea surface salinity, but also on the right, the range of in situ observations like Argo, the WOS and now Ghost Ship hydrography, XPT data, more exotic elephant seal data that from CTD loggers and telemetry, all the way to things like ice tether profiler in the Arctic. So combine all of these disparate and observing platforms with a general circulation model that's shown here at the bottom to do what's called basically data assimilation. I'd like to have in a very high level manner show how observations impact data assimilation, and I hope so. I've been told there are many of you are non-experts in data assimilation. So for those that are expert, I apologize for the sort of the simple way that I am going to go about this, but just to show you how uncertainties and errors actually impact assimilation. So first of all, data assimilation, so we've already said, so you could call it as looking at the data through the lens of models. So models, of course, play an important role. And there are different uses, and depending on how you use data assimilation, the uncertainties will have different sort of consequences. So the one is data assimilation for the purpose of parameter estimation, or you could call this a calibration problem here. And so now the uncertainties would be, we'll try to quantify the uncertainties in the parameters that you are calibrating. The state estimation or reconstruction or synthesis problem that considered as an interpolation problem, here you seek the uncertainties in the reconstructed state. So people might be familiar with reanalysis product, or the derived quantities or metrics. So when we say quantities of interest, so in the ocean, for example, we would look at a derived quantity like ocean heat content over a certain box, or transport through a certain sections like AMOC transport or Drake Passage transport or Nino 3.4 index. So these would all be derived quantities, or what Anish talked about, the forecasting prediction problem, which is an extrapolation problem. And there, of course, the uncertainty would be that of the uncertainty in the forecast. And as again, sort of in some ways repeated here, we have a number of sources of uncertainties that basically come into the data assimilation. So the first one is, of course, the observations. We need to specify the measurement error, but importantly, we also, because we are going to consider these pointwise observations in the context of a model, it's the sampling error and the representation error. Then the assimilation scheme itself, there's different algorithms and the implied approximations that each of these algorithms make. And there is the question of how each of these data assimilation systems ingest the observations. Are they pointwise? Are they in hourly? Are they daily averages? And so on. The model, the underlying model has parametric uncertainties or structural uncertainties. And then the boundary conditions could be from external forcing, from uncertain bathymetry, lateral boundary conditions. And then, of course, we'd like to, in this, we'd like to incorporate prior knowledge, and that comes to prior error covariances that makes basically this statistical problem one of Bayesian, sort of a Bayesian inverse problem. So now comes this simple cartoon on how we think about uncertainties in the context of a simple filtering algorithm, the sort of the classical Kalman filter. for reconstruction, so we're faced with a least squares problem, an estimation problem, where basically we're trying to minimize a squared cost function. Y here is observations in space. And we basically look at the misfit between these observation and a simulated quantity. E is the operator that maps from the model space onto the observation space. In short, here we have this function here, and we see we have three ingredients, right? So we have the observations, we have the model, and we have the errors that we are assigning. So that's the weighted least square with the weights. In the general term, it's the error covariance, often approximated by the variances. And a simple figure, let's say if the model was just a linear function, so we have the straight line here. In blue, we have observations that come in at certain points in time. We have error bars here in orange that have a certain size. And we're basically trying to look at this as a least squares problem. Now, for the filtering purposes, so when we don't actually know the true linear function here, well, what we start out is with an initial condition, and basically we're providing a forecast here, and we arrive at this time xb1. At this time, new observations come in, and this is in this blue cross here, and with some error bars. And the new observation shows us that our forecast has a large misfit to the observation. This misfit is in black here. That's called the innovation vector. And so what we could do is to basically have a new forecast that basically places us on the observations. But that's not the right thing to do, because we see that here the error bar is a very large one. So the Kalman filter, one thing that it does, it accounts for all of the errors, the measurement errors, but also the background error, which I haven't shown here, and basically computes sort of an optimal adjustment that's called the analysis increment here in green to produce a new initial condition. From then we then issue a new forecast, and then so on. So we have the innovation vector here that would be the full difference, but then this analysis increment that accounts for the uncertainties in all of the ingredients here. So now we can take an example of what changes when we change the uncertainties, for example, in the observations, right? So look at this carefully here. Now if I reduce my error bar here, so now you've seen, go back here, go back. So large error bars, here small error bars. Of course, this will also change this data assimilation problem. So we're basically now saying the analysis increments should move, in this case here, should move this new initial condition closer to the observations. And so that's what's done here. And so we see that it has an impact on the forecast, or on the estimation problem. And you also see here now that the impact here, you see this on the state. So now I'll go back and forth here, the state going back and forward. And one thing that it points out is also that if you are too strict on the uncertainties, and if you basically what we sometimes call fit the noise, right? So we are thinking that your uncertainty error bars are not realistic. You actually might end up with estimates that are not as good as the ones that have really the true error estimates. So this all basically goes under in the numerical weather prediction community under the analysis. If you do this analysis step to provide a new initial condition, or if you do this retrospectively for purposes of looking at sort of a larger period back in time, that's why we have these reanalysis that basically redo all of these analysis with the same model, quality controlled offline observations and so on. I'd like to do one other different way of doing this estimation or this inverse data assimilation problem using an adjoint-based method. And here, what I'd like to show, because there's a lot of excitement in machine learning, I'd like to actually show you how there is a very strong correspondence between this adjoint-based model calibration and estimation that actually uses a model and the backpropagation-based neural network training method. So what we see here now, here in this panel, we have a neural network, multi-layer neural networks with these layers here shown in blue. We have inputs here at the bottom that are propagated through the neural networks with some certain activation functions here, H1, H2, and so on. And then we have an output here that we're now comparing to known outputs for supervised learning, so we know what the true should be. And the goal now of training this multi-layer neural network is to minimize this loss function, this kind of we call misfit function. This is done through a method that's called backpropagation, and there's a review of this by Jan Lekun in Nature 2015. And what you basically want to do, you have weights that you are adjusting in order to train this network. And the way how you adjust these weights is you compute the gradient of this loss function with respect to all of these these weights, and you do what's basically a gradient-based optimization. So in data assimilation, when we have a model, we don't have sort of neural sort of networks, but we have actually a dynamical physical model. So we can actually do basically something, we can reformulate this in a very similar way, where now these layers are basically this time stepping of the model. L is the model operator that propagates the state from K to K+1. And we have now a model data misfit function that's shown here, here at the top. And we're basically trying to minimize the model data misfit function under the constraint that the model equation should be fulfilled. And that's called the Lagrange multiplier method. So maybe some of you have done classical mechanics, so you might have heard about Lagrange multiplier. And these are actually just adjoint variables. And again, just in the same way, except that backpropagation is now called the adjoint model. It is a model that is the transpose of the linearized model and calculates the sensitivities, again, of this misfit function to all of the independent inputs that you can calibrate. And again, what we are doing is here is a gradient-based optimization of the cost function. So very powerful. And the key difference is that in the inverse method with an adjoint, we are solving a sparse data problem, right? And where the dynamical model serves as the interpolator, or we can look at this in a different manner where we say the dynamical model actually serves as a hypothesis that we're testing. And in case we're not able to solve that optimization problem, and the residual is not basically, it's not white noise, we may actually consider whether we're rejecting the model. The adjoint sensitivities or the dual model state is actually interpretable. And it provides really a causal link between outputs and input that makes this very powerful. In the context of the discussion of interpretable machine learning here, we actually have a inherently interpretable way on how we basically go about this estimation problem. It's very transparent because it's closely naturally tied to the linearized dynamics of the model. The uncertainty in this part, we're looking at derivatives, so gradients, right? So and we can go a step further. We can look at second derivatives, and that's basically has to do with something with curvature. Think about this problem here. You see this red curve in 2 dimensions. In 1 dimension, this curve is very tight, right? And in another dimension, this curve might be very broad. And what that means is, for large curvature means that the observation, the parameter is very well constrained by the observations in one direction, and it's very poorly constrained by observations in another direction. And we can tie this curvature information, or called Hessian, to the inverse of the posterior error covariance, and that leads to yet another very powerful way on how to do uncertainty quantification, where we can estimate how new observation or how different types of observation basically allow us to constrain or to reduce prior error covariance to generate posterior error covariances. So there's a big research topic now, actually, in the computational science community and also in the data assimilation community, that I don't have any time to go into. I just like to finish here with this schematic, where we're basically saying, and a colleague from NOAA now at Boulder, Steve Penny, basically once coined in this paper, Frontiers of Marine System 2019, where basically say data assimilation is the automation of the scientific method. That's of course a very bold statement, but the idea here is that at the bottom, on the one end, we have observational errors. On the right, we have computational models with all kinds of other, like discretization errors. In the middle, we have theory, and we're trying to find methods in which all of these inform sort of our knowledge gain that then basically then leads to decision making. And with that, I finish. I'm happy to take questions if there's time to do so. Thank you.
Okay, thank you very much, Patrick. I would say we could probably write an entire paper on just that. That was very That was very informative. Thank you so much. And I would say that's probably one of the most technical talks. So you get the gold star for that, going really deep into that subject matter. So with that, I want to remind those who are watching remotely that we can use the chat box. Some people are already using that to start entering in your questions. And I want to remind my co-chairs of the session, if you could, because I might have a difficult time capturing everything, if you could start monitoring that and copying that. I have a section in the Kiko chat notes to capture those questions now. So yeah, so the other reminder too is I know some of you have already started doing this. As we are going to have interactions both in this session as well as in the following session, I would encourage everyone who's attending. I know we have at the moment 52 participants. I think it peaked at 57, maybe 10 or 15 minutes ago. But I would just encourage everybody, if you could mark your names down and your affiliations, and if you'd like, even your email, so we can reach out to you offline. There might be not enough time to address every single question that people here have, so it would just be really helpful, I think, primarily for that, but also in case you want to partake in any following conversations or possible collaborations. So with that, we will now transition over to the Q&A. So I'll start with, this is more of a comment that was asked by Jay Perlman. And I'll for folks who don't know who Jay is, I'll just say his affiliation. So he's representing the Four Bridges organization, part of see here, OBPS. I'm not quite sure what that acronym is right now, but he had a question. Oh yeah, so the OBPS is the Ocean Best Practices System Steering Group. So he's a co-chair of that as part of the IOC. So his comment was, or question was, can you address the next paper, the best practices? Basically, can you address your follow-on paper? Basically encouraging us to submit it in the Frontiers in Marine Science Best Practices research topic, because his steering group that he's a part of, that he's a co-chair of, has a research topic in that research journal called Best Practices in Ocean Observing for peer review of ocean best practices. So I put a link to that in that Q&A area so folks can reference it, and so that I, as a reminder to myself, to look at that after the meeting. So it's more, again, just a comment and a suggestion, I would say. But we actually have a technical question, it seems, from Chung Lin. So I'll start by reading what he put here. So the question is the magnitude or seriousness of uncertainty, and this is actually being addressed to Anish. So I think Anish started answering it. But the magnitude or seriousness of uncertainty would vary or amplify with increasing temporal scale of events or phenomena. He agrees that Lorenz's chaos theory gave us an alarming guideline. He believes the current model prediction ability may only up to 2 weeks at most so far. So the question is, do you examine this in your model or data simulation approach? Also, do you perform your uncertainty sensitivity studies, partitioning the IC and model error respectively? So Anish graciously, even though he's actually not with us on the phone, he is monitoring the chat box at best effort, and he was able to see this, so he answered the question, and I captured it here. It says, thanks for the comment. And the question, yes, I personally, and also my colleagues here in the US, as well as ECMWF, and in Europe, Japan, and other centers, do study the impact of initial condition uncertainty only versus model error representation, respectively. There are also studies on the uncertainty growth and error growth from 2 weeks to seasons and longer. Some of the CMIP, which stands for Climate Model Intercomparison Project, some of the CMIP 5 and 6 versions discuss how uncertainty is quantified on climate timescales. This is the IPCC report that captures this also. I can send you more references, etc. So he puts his email address where he can be reached for more on that. So meanwhile, I'm just going to go back to the chat box to see if there's any additional questions. I don't see any at the moment. And so what we can also do is since this is a panel Q&A, I will actually allow folks, if you want to use the microphone to ask your question that way, you're welcome to do that as well. So maybe what I'll do is I'll just pause for a moment and see if anybody has a question.
How much time do we have left?
So we have about 29 minutes in the session. So I do want to allocate some time as well to kind of talk a little bit about what we have in the last, or in the part 2 session. So we'll do that probably in the last 5 minutes. So if somebody could remind me of the time, I might forget, just so folks can kind of know what to expect in the next session. Okay, so we're not getting any chatter in the chat box. So maybe what I could do is I could just start with a question to Patrick. I'm not. Well, I don't consider myself an expert on modeling. I've been exposed to some of those examples you presented regarding Echo. Being a JPL, we have, as you're probably familiar with the Echo, there's a strong Echo modeling group there at JPL. But I would say your presentation is really the first one that I've seen that, and this is just could be maybe my lack of exposure. The first one that I've seen that actually talks about how the adjoint approach is useful in not just the cost model, the cost function reduction, but also potentially in improving the uncertainty. Can you talk a little bit about how that maybe just at a high level, maybe not too technical, but just at a high level, how does the adjoint approach using the inverse method, how does that actually not just, or I guess maybe you could say it this way, how does reducing the cost function actually improve the uncertainty? I hope that makes sense.
I was muted. Yeah, no, this makes perfectly sense. And in fact, so what we and others have been doing for a long time is basically we're reducing our model data misfit to provide what we call sort of an optimal estimate. So when we do that, ultimately we have one deterministic trajectory. But what we have not, and we can, after the fact, we could say, well, we've managed to reduce the misfit of the observations in this point and at that time and so on. But that's not really getting at the uncertainty. So we have not, well, there's two things, right? The one is it's impossible to, to provide in this estimate for each, let's say each temperature at each location, X, Y, and Z, and each point in time, to then quantify an extra field that basically would provide the uncertainty. That's basically just, it explodes in terms of the dimensionality of the problem. So what we are, and this is why many data assimilation projects are stopping sort of beyond basically providing you with the optimal estimate and actually not giving you this posterior uncertainty, basically saying now we've been able to reduce the prior uncertainty that we'll go into the problem with, and then we would use this to have a posterior uncertainty. What this is, to some people, this is called the curse of dimensionality. So if we're estimating a state that is on the order of 10 to the 7, what we would have to do is this, the uncertainty problem is basically an n squared problem. So we would be faced with sort of 10 to the 14 dimensional problem that we're trying to solve. And that becomes just computationally very challenging. And it's really only recently that we've begun within ECHO to basically develop the computational tools that allow us to equip the state estimate, not just with the estimate itself, but with some error uncertainties that actually include, so that are not just ensemble based. So the ensemble would give us a spread of different realization of the model, but these ensembles are not telling us how a specific type of observing systems are able to reduce observation. So for example, we would like to know, how does Argo reduce those uncertainty, or how does altimetry reduce this uncertainty? This is something that can be captured with what I've presented, or actually really only scratch the surface on That's the this idea of using basically derivative-based UQ. That's a very recent effort, and that's why you haven't seen it yet at JPL. But let's say over the next, I would say 2 to 3 years, there will be more coming forward on this front. And this also relates to quantitative observing system design, because that also the same framework and machinery allows you to say, well, if I place my observational asset somewhere, at a certain location, this has the maximum impact on reducing, for example, uncertainty. In the numerical weather prediction community, this goes under the notion of targeted observation. It's been around for a while, and in fact, Ed Lorenz, the famous Mr. Chaos, and Kerry Emanuel wrote a paper about this in 1997 on the use of targeted observation to say, we're trying to find in a forecast the maximum error growth, the pattern of where is the most likely error growth. And if we can compute that, we can send sort of an observational asset specifically to that location, and it would have the maximum impact on reducing that uncertainty.
Well, you've just blown my mind with that answer. Thank you very much for that. And we have another question for you, Patrick. This one's from Jay Perlman. The question is, what are the outcomes of the OceanObs 19 uncertainty session, and how do they relate to our discussion here?
So the outcome of the uncertainty quantification session was basically just a set of 3 recommendations, and based on these 3 recommendations, the answer is really much more work has to be done. And in fact, the outcome might be, you might call this as there is a now US CLIVAR working group on ocean uncertainty quantification. And that US CLIVAR working group has several purposes. The one is to actually, provide some definitions of what uncertainty actually means. So what do we mean by uncertainty quantification? And I've alluded to this, that different people refer to this as different aspects. There is potentially some statistical illiteracy on, how do you compute certain quantities, and developing some best practices for uncertainty quantification is one of those outcomes. Another outcome is, in some sense, what I described is the real need for modeling efforts to improve sort of more and encapsulate and incorporate formal methods for doing uncertainty quantification in both the modeling realm and in the data assimilation realm. In the data assimilation, it's been already quite developed, because we are on the ocean side, we're basically always learning from the data from the atmospheric numerical weather prediction. We're always so generically 10 years behind, but so we're learning to do this. But yeah, so the pure forward modeling community, if you take the ECMWF suite of models, for example, and the ocean components, it's perhaps, arguably you might say there is not much beyond the ability to say there's an ensemble spread, but we're not able to say how, for example, the Argo array has been able to, for example, reduce uncertainty in the ECMWF models. That hasn't been really quantified yet, I would say. So these are some of the outcomes of OceanObs 19, and I'm happy to point you to the US CLIVAR ocean uncertainty quantification.
Yeah. I hope it's okay to say that, but maybe this is a good opportunity to let folks know that one of the other key outcomes is the establishment of the US CLIVAR working group on uncertainty quantification. To my knowledge, and correct me if I'm wrong, Patrick, but that working group came out of that session, correct?
That's correct. Yeah. Mm-hmm.
Okay. So it's a pretty new working group, and I would imagine there's going to be some overlapping opportunities for collaboration with that working group through having people like yourself. And also, I want to point out that Anish is also a co-chair of that new working group. So just in case people are wondering, and I myself, I'm a participating member as well as you, Patrick. So it's interesting that we have 3 of us here on that related to that working group. All right, so we have some more questions trickling in the chat box. So this one, I'm gonna probably field this one to you, Patrick. This is from Steve Young. It says he has a question related to UQUC is related to a rare but significant events. I guess rare but significant events in general. And the one that he cites is the Chelyabinsk airburst. Does that ring a bell?
And I'd be happy to try to clarify.
Oh,
This is a
Thank you.
weekly formulated question, but I sort of followed when we're talking about what I would call continuous processes, where there's an ongoing process that we understand to some degree, but we do see these, thankfully, usually rare, but sometimes very dramatic events. Chelyabinsk was a small asteroid that did an airburst over Russia to rather dramatic effect. An example that might be a little bit more appropriate here would be an unexpected underwater volcanic eruption. So what I'm trying to drive at is the confidence level of the ability to detect an unexpected event, and can you characterize uncertainty when it's a discontinuous event? That what's the probability of being able to detect and characterize that sort of discontinuous event? I hope that makes sense.
Yeah, I mean, it does make sense. I mean, there's a couple of answers to that. The one, in fact, we don't actually know much about the impact of subsurface volcanic eruptions on, for example, ocean circulation. It's very hard to measure, and that's part of the problem, of deep ocean measurements, that we have so few of them. But actually, surface, volcanic eruptions are actually very important in changing, or in, as a externally forced variability of ocean circulation. Take the Pinatubo eruption in 1992. That has a major impact on the atmospheric circulation, of course, and that in turn had a major impact on almost a decadal timescale in changing sort of forced ocean circulation changes that can be clearly attributed to the Mount Pinatubo eruption. So it's a discrete event, and it has, in that sense, the discrete event, the ocean being a memory of these, let's say, sort of point-wise perturbation in the atmosphere, and integrating those to actually have ocean circulation changes on a longer scale. Now, the second is, of course, the rare events and long tail events are always very difficult, and these are all grouped under the notion of, like volcanic eruptions, these are externally forced events, right? So the question is, do we have, in a statistical sense, do we have a distribution on the timescale of which we anticipate such an event? Can we say from the past that every so and so often in the mean we will expect sort of a volcanic eruption or other types? And that would be nice to have. I would argue that for some of this we have that, and for some of them the observational record is also sparse to allow us to make such statements. And all of this has to be seen against the background, the internal variability of ocean circulation changes, and the sort of the paradigm model here is kind of the ocean or the coupled climate system as a Brownian motion, right? So you think of the atmosphere being sort of fast fluctuating random noise that basically hits the ocean. The ocean integrates that very fast noise and creates its own lower frequency, sort of longer timescale variability. And the model is that like a Brownian, like a large molecule looks like it's doing something deterministic, but it's actually just following sort of the path being hit by these high frequency molecules. So even if there are these distinct events, they are competing in terms of their detection against the other noise that's sort of present in the ocean. So that's a tough problem.
Thanks.
Thank you. Yes, and we do have some additional questions that have trickled in. So this is probably a comment and a question. This is from Carrie Pulliam. This is, I think, just to anyone who can answer it. So it says, I've enjoyed the presentations, although this is a bit beyond my work. What does the panel recommend for representing uncertainty caused by multiple scientific interpretations? I'm thinking specifically of subsurface geologic data and the subjective nature of picking those depths based on based upon a geophysical log or samples, but in general, data uncertainty that is created by multiple interpretations. Can you quantify that? So I can start a partial answer to that, and then I'll hand it off to Patrick. I would say this gets into the realm of use cases that we were trying to look at in our first white paper that was published back in November, looking at different perspectives, including mathematical, observational, and the user perspective. This, to me, sounds like a user perspective example, and it gets to a very specific example, which unfortunately, for the scope of the first white paper that we had, we didn't have a very specific use cases on the user side that gets to this level of specificity for the types of data where we and the types of questions that we're trying to address. And I think it's an interesting one because you're talking about multiple scientific interpretations and the uncertainty associated with that, and a user trying to make sense of that. So I would say, if you're interested, send me and all of us an email, myself, my co-chairs, an email offline, and we can try to engage you for our part 2 white paper, because our part 2 white paper also, in addition to trying to provide some best practices across the board, across all different earth science domains, we want to try to also capture use cases that we didn't yet already capture. And I think this is a great example of that. Patrick, did you have anything you wanted to add to that?
No, I mean, I'm not sure about the specific geological data on the oceanographic side, but maybe one thing I would frame what you're getting at maybe as a problem of detection and attribution, right? So the example being, the famous hiatus or surface warming slowdown, and what is it? What are its causes? And that may be something, if I interpretation problem. So there are different interpretations of an event. What could it be? This is actually something that one can try to quantify, and that whole field of trying to quantify and actually either, it's kind of a way of hypothesis testing, just at a large scale, is one of detection and attribution. That's a well-developed field. Event attribution, even extreme event attribution, is a highly sophisticated field in the statistical community that deals with statistic of climate variability.
And as we were both talking, I saw that Anish also tried to answer Carrie's question in the chat box. And so his answer is that we can represent the different physical scientific interpretations in a model of that process using stochastic processes. So stochastic modeling, as he talked about in his last talk, is a relatively new but widely studied applied math field. And there are techniques from that field to represent the various interpretations, uncertainties using stochastic equations. So, and then Carrie responded saying that she'll reach out to us by email for further conversations. So thank you for that. I'm sorry, that's from Carrie, I should say, but Anish answered the last one. So thank you, Carrie. All right, so it looks like Chung Lin has another question. So thank you, Chung Lin. By the way, Chung Lin is one of our very active members, and he's also one of our co-authors from our 2019 paper. So, Chung Lin has a remote sensing background, as well as I think a bit of a data assimilation background too. So this question is for Patrick. It says, thanks for the informative, technical, and great presentation. Just one comment that regarding the second. One comment on, and it sounds like he's agreeing with this, on your final quoted bold statement, data assimilation is essentially an automation of the scientific method. He says, through applying a suite of genuine scientific observations to properly and effectively improve model predictions is by all means scientific. So it sounds like he's agreeing with that statement. Chung Lin, I'm gonna invite you to speak. If you want to turn on your mic, did you want to have anything you wanted to add to that, or?
Thanks, Dave. Okay, I try to be quiet because I'm so audacious, right? I'm not active in data, okay, but because I have a scientific background in dynamics and also knew a little bit about the chaos butterfly effect, so that's why I chime in some scientific concept. Thank you. Anyway, very good. Kind of remind me, okay, back to the good old days. I also have some mathematical well, practicing myself. Thank you. Very good. Thank you, Dave, and all our folks.
Thank you, Chung-Lin. I'm going to take another peek here to see if we have any questions that we've missed. It looks like we've addressed every one. I'm going to maybe just pause for another 30 seconds or so to see if anybody wants to chime in, and then we'll move on to our closing remarks.
David, this is Payne. I have a follow-on question to Patrick, if I may.
Yes, please, go ahead.
So he's talking about the rare discontinued events, and my follow-on question is that in this kind of situations, are you talking about uncertainty associated with how models handle the impact of those events, or that in predicting this kind of event?
Oof, that's a tough question. I don't think there's any way that a model can predict the event, right? So think of volcanic eruption. I mean, we cannot predict the onset, occurrence, magnitude, or position of a volcanic eruption. So the only thing we might be able to do is to say, what if, right? So we can ask what if questions in the sense of, if there was an eruption, how would it change atmospheric circulation fields, and how would the ocean respond to that? It's not an easy problem to do. And for a longer term, so what I was thinking more in that context is that on climate timescale, so if you are trying to look at sort of a millennial climate simulation as a control run that tries to represent natural and natural forced variability, then what you could do is you could basically say, based on on the likelihood of such an event, you can actually provide forcing, stochastic. Actually, that is part of the stochastic manner. You can put those into the forcing functions. But anything that's sort of extreme and rare events is very difficult, right? So the same on tsunami prediction. Of course, once a subsurface, a deep earthquake has happened, you can then run a tsunami model, and those are very good. But you cannot predict when that tsunami when it occurs. I mean, again, but you could again ask what if questions, and in fact, from a computational perspective, you could begin to build up a database, and which allows you to maybe have a quick look. If you pre-compute solutions, plausible solutions, you might be able to extremely quickly react to this without having to run expensive models. So these are some of the thoughts.
Thank you. I really enjoyed the presentation, both of them, and I'm looking forward to the discussion in our part 2.
Thank you.
This one, can I comment on answer the question? So I did have some knowledge about this. Just like I comment in the niche. Well, the prediction itself is really difficult. So that's how the Lorentz canvas with the butterfly effect, the chaos, even the initial condition, a small change may drop to a very infinitive answers. Because again, the bottom line is that many phenomena occur. They are necessary conditions, not really sufficient conditions. So even under the certain sufficient conditions, if you follow that equation going on, may not go to the result you predict. So that's even now, say people even can probably predict the weather up to most. Some people may claim they can get to 30 days, but still, okay, that's a very questionable. And also that's the reason why data simulation kick in. Okay, so they do kind of guide the model, okay, through the changing with the updated observation to guide the model forward. So that's the reason why even a small change in the initial condition may not, okay, may change a lot of in the outcomes. So currently, even though you say something, you see some Earth was vibrating, then you may not could just predict it to a volcano in the end, because but you can do the diagnosis at all. When you do see something happen, then you can kind of trace back to what's the original condition there. But if you try to reverse it, may not be easy to do that, okay? Especially under our current numerical modeling. But definitely the power of the computer now do help to bring in the data simulation to help on this.
Thank you, Chung-Lin. So we're now at the 5-minute mark left in the session. So I just want to say that I just want to thank the speakers again. Thank you, Patrick, and thank you, Anish. for agreeing to take part in this conversation. It was very valuable information and insights that you shared with us that I think personally my mind is blown. I still probably need to rewatch this about 2 or 3 times to really understand the full implications of what the technical aspects are to uncertainty quantification and so forth. So thank you again for that. I want to say that there is there has been, since we've been speaking, additional chatter in the chat box. I will say that keep doing that. It looks like people are interacting with each other. I would say keep doing that. This Zoom Zoom session will stay live. It'll stay ongoing, even though the session will be ending in a few minutes. It'll stay going, and it's going to be the same exact Zoom link as our part 2 session. So when you come back and join us in part 2, you don't even have to, if you don't want to, you don't have to leave this window. You can keep it open in your background or something, and then come back with us in about 30 minutes and rejoin us. With that, I'm just going to briefly share my screen here in a second, just to talk about where we're going to go next. Let's see here. This is the right one. Okay. All right, so hopefully you can see what I'm sharing. So this is just a preview of the part 2 session agenda. This is going to be more of a working session. So this is for people who really want to go into a deep dive conversation. It sounds like there's people that are already doing that now, which is great to see. There's a lot of enthusiasm about this topic and all the ancillary topics therein. I do want to say that we're going to continue the modeling and data assimilation discussion in a very specific breakout Zoom room where Gepeng is going to lead that breakout. And so I've also invited Patrick to facilitate Peng in that breakout as an expert facilitator. Anish is welcome to do that one as well. I've also invited Anish to take part in the breakout 2, which focuses more on the suborbital and in situ. So Yaxing Wei will be leading that one. And then Rama will be leading breakout 3, which will be best practices for producing UQ, UC information. And then Bob Downs will be leading the breakout for the interpretation and the usage of UQ, UC information, which seems to address one of the questions that was asked later on in this current session. So there will be about 35 minutes allocated for those deep dive mini breakouts, if you will. And we'll have a summary debrief where we come back and join each other in the plenary Zoom instance, and then we'll summarize our takeaways from both sessions. So with that, it looks like we have a couple minutes left. I'll just close for now by saying thank you again for joining. Also, you might be wondering to yourself, how is it that I will join one of these mini breakouts once they come back? So the way that works is you'll notice that what some of the leads have already done is they've modified their names in the Zoom window. And the way you do that is you click on those little dots. I'm going to stop sharing my screen now, but you basically click on the little 3 dots at the bottom of your Zoom window that says more, and that's where, I believe that's how you do it. I think, or unless maybe Megan, if you want to jump in, I think I may have forgotten.
You can also click the participant window, which if you don't have it open is an icon at the bottom of your screen, or should be. And then to the right of your name, you'll see a button that says more, has a little drop down. And there you should be able to rename yourself.
Right, and then what you'll do is you'll just add a number. Thank you, Megan. And you'll just add that corresponding number to the mini breakout Zoom room that you want to be part of for that deep dive discussion. I will say this, that once you join, you can leave, but I don't think you're going to be able to join a different room, or at least you won't be able to join a different mini breakout, is my understanding.
Actually, what you can do is the host will stay in the main room. So if you don't like where you are, you can come back and the host can put you in another room. But it's great if you can put that number at the beginning of your name. That way it's very easy to sort you.
Thank you. And then everybody, once it's over, there's going to be a time limit. So once it is over, everybody will automatically be forced back to the main room. once that's over. And as myself, I'm going to be kind of like roving around in different rooms periodically, just checking in and contributing to some of the discussion. So with that, we're at the end of the session now. So thank you very much again, and we'll see you at our part 2 session. Thank you.
And one more thing, David, for those who are watching the live stream, you can participate in the breakouts, but you will need to call in by phone. We can't, obviously, we are not able to live stream the breakouts to YouTube, but if you call in with the number that you have, we can put you into one of them.
Okay, thank you.
One more point is we do get the warning about 5 minutes before the breakout ends, whatever time we set. I think it is 5 minutes. I don't know.
Yeah, is that going to be a 5? Okay, so it looks like we're just waiting on Bob Downs to join. I don't see Bob on here yet. I'm going to check my email in case he's having problems. I'm not sure if he... No, everything looks good there. Screen with some just housekeeping agenda items real quick. Is it possible to start recording this now?
Yeah, I'm going to do it right now.
All right, thank you very much.
Live.
Okay, let's go to my agenda. All right, everyone, welcome to our part 2 session. As we closed in our part 1 session, I kind of gave a little preview of this. So I just wanted to spend a little bit of time, a few minutes, just introducing what we're going to be doing in part 2. As Dan mentioned, we're going to have mini Zoom breakout sessions. So we have these various perspectives that we're going to, I'm going to introduce what they're going to be talking about. And as we go through this list here in the next couple slides, if one piques your interest, what you're going to want to do is change your name on Zoom, and you can do that by clicking on the participants box and clicking on your name, and you can change your name that way, and just add the number of the room that corresponds to the one you want. And you're going to see that others have already done that, and so just if you could just follow that same format, and that'll make it really easy for Dan on the back end to assign those of us who want to be in certain rooms to those rooms in a timely manner. So we're going to go ahead and just introduce what each of these things are. But before we do that, just capture some goals of the session. So what we're really going to be doing here is in this deep dive working session is capture these inputs that we're going to be getting from these different topics, and use that to basically provide kind of an outline and a set of preliminary consensus statements that we'll use to start drafting our part 2 white paper. And what we also want to try to do is capture a more comprehensive set of perspectives from what we already have. And this will really help us more fully understand how UC information is both generated and utilized in a more broad context than what we did previously. And some of the perspectives that we want to place a little bit more emphasis on today are, as I had mentioned in the first session, suborbital in situ modeling and data assimilation. The third objective is to identify some best practices, and this would be for both the estimation and packaging of QUC information, and secondly, for the dissemination, interpretation, utilization of UC information. And last but not least, we're hoping that there's enough enthusiasm surrounding these topics and surrounding the high-level objective of having inputs for the white paper, where we can get a coalition of committed people that can be willing to contribute towards this new white paper. Okay, so we have these mini Zoom breakouts. I'm going to call this breakout number 1. Peng is leading this one, and this is continuing most of the discussion from the last session on the topic of modeling and data assimilation. And so just in case everybody is wondering, Is it possible to review the slide material while I'm in this? The answer is yes. You can access the slide material both in the Kiko chat notes page as well as in the SKEB agenda page. The presentations you'll find are in both. There's also presentations from the winter ESIP meeting that are in the Kiko chat page exclusively that I made available for folks who want to revisit that. So we really want to try to here focus on that part one session, but also we want to invite outside perspectives on the subject matter. So those folks are also welcome. I know there's a number of people that joined, especially in the last session, who also had a not just an area of interest, but they had some expertise on data assimilation and modeling. And so we welcome those perspectives as well. We want to also try to identify the common approaches in producing UQ-UC across all the different types of modeling that is being in assimilation is being done, and then also try to capture key challenges that are being faced by the data producer side as well as on the user side. And then lastly, we want to try to consider how this information in both model and simulated types of data is different from observational data. So that takes us to our Zoom breakout number 2. So this will be led by Yaxing Wei. The focus here will be on suborbital and in situ data. I know Anish touched on some of the in situ examples in his talk, but largely this is going to be a continuation from what the outputs were from the 2020 winter meeting. If you did not attend that meeting, or if you're a little rusty, if you attended it but you're a little rusty on what was presented, again, those presentations are in the Kiko chat. If you scroll down, you'll find there's a section called related presentations, and then you'll be able to find the links there. So the 2 presentations that you'll want to look at are one by Fred Bingham, covering suborbital and things with regard to S mode. And the second one is by Mikhail Kusela, which will cover examples, in situ examples, specifically with regard to Argo float data. And again, as usual, additional perspectives on this subject matter are also welcome. So if you have something else you want to contribute beyond what was previously discussed, those perspectives are also welcome. We do want to try to likewise identify common approaches in producing UQ-UC. So we want to try to converge on some commonalities. And also we want to look at key challenges that are being faced both on the producer side of the data as well on the user side. And we want to think about also how there's a lot of people out there that seem to think that there's a significant distinction between methodologies and techniques with regard to estimating UQ and UC that are different in airborne and in situ versus space-based remote sensing. And so I think it's important to call those things out, but I think it's also important to see where there's some potential for overlap of methodology and technique, and maybe even overlap on the user side, especially for people who do things like data fusion activities. When you're doing a lot of data fusion, you want to try to identify techniques of both estimation of UQ as well as the interpretation and application of it for your research that is consistent across all the different types of observational data that are out there. And then now we have the Zoom breakout number 3. This will be led by Rama. And then this is our segue into actual best practices. So this is for folks who are really interested in trying to establish best practices. But this is actually going to focus more on the data producer side. We're going to have a number 4 that'll go into the next slide that'll focus on the data user side. That'll be Zoom breakout 4. But on the producer side, we're going to be using our November 2019 white paper as a baseline for that. As mentioned previously, additional perspectives are also welcome. Again, trying to focus on identifying a common set of best practices here that are applicable across all the different earth science domains. So you might have a particular expertise in one earth science domain, but try to be sensitive that other earth science domains might be new to that perspective, and try to think of a way to build a bridge that can apply some commonality that is relatively ubiquitous in its application. Another thing to think about too is how UQ-UC can be more optimally packaged within the data files. This is something that's oftentimes ignored by data producers. But I think more and more data producers are starting to become mindful of the need to do that. It's just a question of how can it be done more optimally and in a more standardized approach. And lastly, we want to try to think about identifying some common pitfalls to avoid as a data producer. And with that, we'll go into summarizing what we want to look at with the best practices in using UQ and actually using the UQ-UC information. And this is going to be led by Bob Downs. Again, we're using the 2019 white paper as a baseline. Again, welcoming additional perspectives. Again, we want to try to identify a common set of best practices in dissemination, interpretation, utilization of UQ-UC information, and think about it in the sense of making sure it's applicable across all the different earth science domains. Another thing to think about is consider ways in which we can try to reduce the learning curve and improve correct interpretation for those who are non-scientists, and also think about trying to find ways to identify pitfalls that can be avoided, especially common pitfalls on the user side that can be avoided in making use of and interpreting UQ-UC information. So with that, that's the end of my introduction. Right, what I want to do right now is just segue into maybe what I'll do is I'll just share my Kiko chat so everybody can see what I'm looking at here. Let me do that real quick here. All right, so here's my Kiko chat box. Sorry, you're seeing a bunch of other windows as well. Let me just zoom in here. All right, so you can see that these are the different Zoom breakouts. There's a Google Notes page in the Kiko chat that points to each individual box here. I'm sorry, yeah, that's within each individual section of the Zoom breakouts. And each notes page should be editable. The leads will be responsible for kind of capturing the notes, but all are welcome to contribute to the notes. We want to try to also make sure we capture participants in each of these Zoom breakouts. So you can do that here, but there's also a section within each notes page to do that as well. I want to also remind everyone that if you want to join a particular Zoom breakout, you might have just joined the Zoom call within the last 5 minutes or so. So you may not know this, but if you want to join that, you're going to go ahead and change your name by going to the participants area here. And let's see if I don't think I can do it because I'm in the chat window somehow. Maybe if I do this, yeah. So here's myself. I go to more here, and there's a way to do it. Oh yeah, rename. There's the option. So I just go to rename, and then I can just change myself to 1, for example, and that way Dan knows where I'm going to be assigned. I'm going to change it back, of course, because I'm going to be a co-host, so I'm going to be roaming around to different rooms as we speak. So what I'm going to do is I'm just going to give a few minutes for people to start doing that, start thinking about what room you want to be a part of. Again, I'm going to summarize what those rooms are. Again, so room number 1 is data assimilation and modeling. Room number 2 is suborbital and in situ. Room number 3 is best practices for producing UQ-UC information. And number 4 is best practices on using UQ-UC information. So I'll give folks a moment now to start changing their names. And let me know if there's any questions or if you have any issues. So it looks like there's a few people here who haven't yet put a number to their name. So I'll just give those people a little bit more time to do so. And yeah, feel free to maybe raise your hand or I guess just post something in the chat window if you're having an issue, or you're welcome to speak up too with your mic.
David, while we're waiting, would it be possible to put the broader goals for the entire session in the chat? I think that was on one of your earlier slides.
Oh yeah, just so we have some persistent capture of that. Yeah. It's also, by the way, those slides are also available in the, if anybody wants to look at them on their own, I can do that, but they're also available both in the Kiko chat as well as in the SKED agenda page. But I'll be happy to do that.
Well, thank you.
Looks like I just have 3 people now without a number next to their name, aside from David.
In that case, I think you just assign them randomly.
All right, I will do that.
I guess if you should mention that if people are not happy with the way they are, they can go back to the main room and get reassigned to something else.
That's a great point, Rama. Yeah, just if you aren't happy, you can always exit at any time, I believe. And if you have any issues with that, just use the maybe the Kiko chat area, and somebody can get help you with that. So Dan, we're at I think the right time now to start the room. So we'll just wait for whenever you're ready.
I'm all set up. So we're going to run for 20 minutes before you'll get a notification saying that there are now 15 minutes left in the session. Another notice 5 minutes before the end of the session. And when the session actually says done, you actually get another 60 seconds to say the very last things you have to say before you'll be kicked out of the room and brought back to this room. If we're all ready to go, then I'm going to click right now.
Sounds good. Thank you.
All right, you should all have an invitation now to join a room.
So Dan, if you like, you can put me in the second room as a starting point.
All right.
Thank you.
Yep.
Okay, so I think people are going to start trickling back. Anish, can you hear me okay? Okay, yeah, here's everybody. Everybody's coming back now. All right. When it rains, it pours.
We are not back.
And thank you again, Dan, for that help. That was excellent. It worked out
My first
beautiful.
time flying this plane, so I'm glad everybody survived.
All right, so I think what we'll just go ahead and do is we'll do the debrief in order of how it broke down. But because additional time was allotted, I'm gonna ask the speakers to consolidate their debrief to about 5 minutes. I'm gonna give every debrief speaker who are the leads of these these breakouts, I'm gonna give them about a 1 minute warning when they're speaking if they're getting close to that time. So with that, we will start with Peng. You can go first, Peng.
Okay, thank you. And I'm going to share. Do everybody see my screen? Okay. We have discussed various different aspects, and here are some of the main points coming out from very interesting and exciting conversation. One is that it's always good to capture whatever we can with observations, and that acts as input to model or forcing to model. And the second point is to provide users with what we know, even if we may not know everything, but provide them whatever we know about sources of uncertainties and errors. And the cell level information is very important. That's one of the reason the work David and other group on the NICDF, that's on information on the cell level. And the third one is that use model whenever we can. When we can, and especially they can be utilized to produce ensembles to estimate uncertainties. But we need to be aware of model limitations in terms of the physics and other factors. So for the modeling community, they like to have uncertainties in terms of numbers, and with enough context for them to understand what that means. The last point is recognize the fact the uncertainty estimate is a complex and a complicated, requires a complicated computations, and it would like to need dedicated resources. And that's all for now.
Thank you, Beng. You're way ahead of time. So maybe I'll invite some time for a question or two for Peng if anybody has one. And this time, I think if you have a question, feel free to just speak up on your mic. There's not very many people on the line right now, so you're welcome to just say your question out loud.
Oh, that's good. That
okay, looks
like yeah, clear.
All right, good job capturing all that. And we will. I want to first check in and verify if Yaxing is ready. If not, we can move on to Rama. If you need more time, Yaxing, just let me know.
Yes, probably a few more minutes would be helpful.
Okay, we'll have you go at the end. No problem. All right, so Rama, you're welcome to go next. Thank you.
So I could share my screen also, I guess. The question is, which thing should I share? I'll just share the screen. So can you see my screen? Can you see the?
Yes.
Yeah. So we had just 3 people in the group, and David was roving. Of course, he came in a couple of times. So our discussion was, well, there is the summary debrief statement. So overall documentation and propagation of uncertainty from provenance throughout workflow is needed. And so if uncertainty is often difficult to propagate and is done as an afterthought rather than as part of the overall analysis process. So that means we need to have broad implementations that follow best practices in quantifying uncertainty, regardless of field. So at an abstract level, we need to have processes that help propagate uncertainty through workflows. And the responsibility for generating and propagating uncertainty belongs to two groups of people. One is algorithm software developers who develop the scientific algorithms and also the workflows that generate the products, as well as developers of programming language to have proper tools that can be reused. And making things open source and encouraging people to use them is a very useful thing to do. And abstract representation of workflow and provenance that's independent of the domain and implementation can be used to provide a standard and extensible way of representing uncertainty information. And an ontology is needed that can capture a variety of types of error in a standardized way that works across data sets and disciplines. So that's primarily a summary of our group's discussion. We had a lot of interesting points that were made.
Thank you, Rama. And just since we have another minute and a half left in your time allocated, we can maybe have a question or two if anybody has a question.
Like Rama, I have a question. This is Ed. Do you really need an ontology to describe the errors or just some common vocabulary? Ontology seems like a little almost an overkill to me. Can you comment on that?
I think, Joe, you're the one who was pointing it out, so go ahead.
Probably just a vocabulary.
Yeah, thumbs up for that.
Yeah.
Okay, thank you, Rama. Are there any other questions or comments on this one? All right, in that case, we will move on next to Bob Downs. Bob, are you ready? If you're trying to speak, Bob, your mic might be muted.
Sorry
Yeah,
about that.
Oh yeah, there you go. Now I can hear you.
Yeah,
No problem.
I was looking at my notes there. Okay, so we had 3 of us in the group, and that was Johan, Douglas Rao, Ed Armstrong, and myself, and then David came and joined us periodically. And so we were taking the user perspective on this. And the first thing that we did is did a brief overview of the uncertainty paper because everybody wasn't familiar with it. And that gave us a little bit of a background to move forward. And then after that, we started talking about, in terms of perspectives, the audience, and in particular, experts versus non-experts. And so, for example, the challenge there would be what information would facilitate understanding by non-experts. And then when we start to talk about experts, we might think about their disciplinary challenges, because different disciplines will use the uncertainty information in different ways. And they also might have different purposes for using the uncertainty information. So that's also another consideration. That is, what does the user do with the uncertainty information to interpret it? And then relatedly, Douglas was telling us about a study by Kenny out of the University of Minnesota. And they had done a study to determine best practices for communicating climate projections. So that might be something to review when preparing to write the paper. In terms of best practices, we didn't do too much there, but we did talk about representation as graphs, and that might be more applicable for expert audiences. But for non-expert audiences, pictorial representations might be appropriate. Likewise, for both groups, colors could be important, and using uncertainty information as a filter might be appropriate when using satellite data. And the communication of the sensor and the algorithm also might be necessary to facilitate understanding. It might be a challenge when conducting data fusion, and we need to standardize how the information is represented in the data files, and how we might want to, or who would be able to use quality flags, for example. Could non-experts use quality flags? And whether that could be a filter against confidence levels. And then finally, regarding the committers, we had talked about there was a comment in the chat that somebody was asking whether we should have a targeted journal instead of a white paper, and we talked about that, and we were kind of thinking, that might be a good idea. And then for committers, we have 3 of us, Ed, Douglas, and myself. So did either Ed or Douglas want to add anything?
I think you covered everything.
Thanks.
That sounds good.
Thank you, and you did it right on time, Bob. Thank you for that. But we do have a time, maybe if there's anybody wants to ask Bob a question, so we'll allow time for that as well. All right, it looks like you're off the hook, Bob. Thank you. All right, so we'll circle back to Yaxing if you are ready, Yaxing.
Oh, sure. Thanks, David. Let me share my screen. Okay, so we had a number of participants in our breakout room. We have Renee, we have Evan, we have Jacqueline, and also Anish. And we had a great discussion. We talked about the challenges a lot, which I will talk about. I'll highlight a number of the discussions, the outcomes that we had. So as I mentioned, we talked about the challenges a lot, and we slightly touched on some potential solutions. So we have 4 objectives for the breakout discussion for sub-orbital and in-situ data products. So the first one is the common approaches taken to produce UQC information for such type of data. And we talked about those different aspects of the uncertainty information, like the geolocation uncertainties associated with LiDAR observations, and also the spectral uncertainties associated with imagery observations. And even mentioned that one good solution is to involve ground validation, and actually enough and more ground validation to better capture and also improve uncertainty associated with those in-situ observation, the suborbital observations. But unfortunately, such ground validation information is rarely achieved, and the validation points are typically sparse. Another topic I want to bring up is we came to a consensus that it's a typical need to create graded products from ground-based in-situ observations. And Anish gave an example for the ocean observations, and the same need and the same challenge applies to the land observations. Like the Ornodeck has the daily meteorology data graded product created from ground in-situ observations. And the need for pixel level or the grid level uncertainty information or the error bar is a typical need from the user's perspective, and very important for many applications, including decision-making. So the second objective, key challenges faced by data providers. We had a lot of discussions on this, and I think we agree that compared with satellite missions, which are typically resource-rich and more focused in terms of the number of the observations made, suborbital and in-situ observations are typically much more broad and contains many instruments and many types of observations made. Like one airborne observation can make like hundreds of measurements. And another problem with in-situ data is that the proliferation of low-cost sensors, which introduce different levels of uncertain information. And we also link that to challenges faced by citizen science data products, uncertainty, quantification, and characterization. And then coming back to the user's perspective, we discussed that sometimes.
1 minute warning, just so you're aware. 1 minute.
Sure, thanks. Data being used incorrectly by users due to mistaken assumptions made by users due to the lack of the knowledge that associated with the observations that tells users the contextual information or the metadata associated with the measurements that was made. And it's a need for the user perspective to have access to this kind of anecdotal information to capture such context and metadata. And then the last objective, and we, I think, agree that in-situ data is very challenging compared with satellite observations.
Thank you. Oh, is there more? Okay, go ahead.
Sorry, if I miss anything, feel free to bring them up. Renee, Evan, Jacqueline, and Anish.
Thank you. It sounds like there's a lot of overlap between what you've talked about and what Bob's group talked about. So I think it would be beneficial once we start getting to the point of drafting the white paper, I think for those two groups to be interacting with each other. Great outcomes there. Are there any questions for Yakshing before we move on to our closing remarks?
Yes, this Xiongling, yes, I have a comment. Okay, yes. Yeah, I think very good presentation there. In terms of the satellite data and also in-situ data, I think besides the uncertainty of the instrument itself, okay, I think the data sampling problem should also be considered. Even say some satellite data and the in-situ data will forget their own uncertainty there. But when people try to co-locate them, so the sampling, the region, the grid point, and I think that's probably also a concern, okay, should be in this. Right.
Thanks, Xiongling, and I'll put that down.
Thank you, thank you.
Thank you.
Yeah, this is more like yeah, it's not the instrument error, just due to they even try to compare them together, and yeah, how you're going to sample them, that's kind of an art. Thank you.
Thank you.
Thank you, Yakshing. All right, so I'm going to go ahead and, if you don't mind, I'm going to share my screen in a moment here. As what I'm going to do is we're going to talk about some of the key takeaways, and I think this is something this is an exercise we can kind of all do together. Let me go ahead and share, as we have about 10 or so minutes left. All right. And here's our Kiko chat area. All right, so as you can see, I captured one takeaway, and this is just because this is a two-part session. So I wanted to capture at least one takeaway from the first session, and I defined it as to look into new use cases, particularly capturing modeling, assimilation, and end user perspectives on implications of uncertainty on multiple interpretations of scientific assessments. So does anybody object to that, or maybe want to improve the way that that's worded? And if you'd like to speak to it, you're welcome to use your microphone, because I'm actually not monitoring my chat window at the moment. All right, I don't hear any objections. And
I think the sentence is too long.
It's too, okay. All right.
I just cut it off after implications of uncertainty, or call it implications of scientific uncertainty and error assessment or something like that. I don't know.
Yeah, I think I wanted to include this other part because this came up as something that we never really explored in the first white paper, this multiple interpretations of scientific assessments. And I didn't want to make this one its own takeaway item, just because I wanted to leave room for other takeaways. But yeah, what I can do is I can just highlight. Can you hear me okay?
Yeah, I guess you have your reasons, is what you're saying.
Well, yeah, it's just more, somebody brought this up. I want to say it was either Carrie or Jessica that brought this up in the last session. And it was a very key, I thought it was a key item that we hadn't really looked at all. So I just want to capture it so we can have an investigation on it. We can put some earnest investment into that. All right, so let's move on to maybe so what I'll do is I'll allocate these two other ones for, because we're only limited to 3 here, to what folks want to contribute here. So what I would like to do here is maybe for number 2, maybe have a takeaway that's common between Peng's session, which was on modeling and assimilation, and Yakshing's session on suborbital and in situ. So maybe I'll let either of you respond, and I can just jot down the thoughts and we can come up with a better way of saying it later. But whoever wants to go first, maybe just think about what are some common issues that you think both of your groups could resolve together. Common issues that you both share. Think about it maybe that way.
There are a number of items are overlapping. One, I'm not sure whether that will be key way. Patrick and Chinling, please correct me or join, chime in, is the scale difference between in situ and satellite, or it's more like in situ and spatial data.
Thanks for bringing that up, and I agree with you. I think in our discussion, the example that Anish brought up is a very good example that shows the connection between the in-situ observations and the modeling and the simulation products. Like, it's a very typical use case of leveraging in-situ observations and bring the data into the scale that would match the modeling and the simulation product. And so basically the in-situ observations would be an input, but during that process, there would be a resampling or regrading process that would introduce an additional layer of uncertainty information.
Okay,
so I'm going to add to that. Let's see here, common ways of resampling, or I'm just going to, for lack of a better word, I'm just going to say data fusion applications. But what does everybody think about sort of just the high level statement here?
There might be uncertainty associated with that resampling to data to move from one scale to another.
I'll probably just say uncertainty due to data resampling. Yes.
Yes.
If you put a symbol, right?
Yeah.
Or precision-wise, or comparison, or whatever usage. Yeah, I think this kind of you can just generalize as a data resampling error, okay, something like that. Right? Uncertainty due to data resampling.
In the data assimilation context, some of it is often captured by the notion of representation error, right? And there's an entire paper that's been written about this that I can try to dig out and forward, that I'm not involved with, but representative error, representativeness error, or representation error is basically what is a certain data set, like a point measurement versus a retrieval versus a footprint, right? So a satellite has potentially a footprint, that incorporates noise and the signal. And then, of course, the model itself has a scale that it represents, and then smaller scales that it does not represent, and therefore the model should not be expected to have those features that are in the observations, and so that can be captured by the representation already.
I think
right,
that
thanks.
would be great to include in the best practices, because
yes.
that's the terminology. I think the community would be beneficial to have that common knowledge.
All right, so thank you for that input, everyone. So we have 2 minutes left. I'd like to allocate those 2 minutes to this third point, and I want to give Rama the opportunity to converse with Bob and think about the common issues or needs that or things that need to be addressed where there might be some overlap between the data producer perspective and the user perspective. So whoever wants to go first on that one.
Yeah. Can you hear me now?
Yes.
Yeah. I think we talked about discipline-independent tools are needed that are open source for facilitating both algorithm developers and, algorithm developers to propagate uncertainty through workflows.
Okay, and maybe think about how this overlaps with Bob's user perspective in some way.
Yeah, so relatedly, we were talking about the disciplines also, and how they might use the uncertainty information depending on their purpose. So I think this is a commonality between the two, the user perspective and the data producer perspective.
Okay. Yeah, I'm just trying to think of a way to tie these together. Maybe the way this could be tied together is that what can satisfy the user's need that you just touched on, Bob, is maybe just having that information consistently represented in the data files. Does that seem like maybe a foundational starting point?
Yes, definitely.
Can I have a question and comment for Rama? You mentioned discipline independent. That's very important, but I just want to confirm with you. Do you mean one size for all, whatever kind of discipline with this tool will be satisfied?
Yes, there should be some kind of an abstraction of it, and we need to have a common vocabulary that we use for talking about uncertainty. And so the open source, like developers of programming languages like R and Python should be providing APIs that facilitate representation of uncertainty and propagation of it through workflows. Is what we're talking about.
Okay, thank you.
Yeah, guys, I would recommend putting
Go ahead.
common vocabulary somewhere in here in bullet number 3. Somewhere we can slip it in there, maybe in the opening statement with open source tools and common vocabulary, because I think that's kind of one of the critical pieces that ties bullet 3 together. Thank you.
Yeah, did you see how I just put that in there for you, Ed? I captured it right here.
Okay. Yep. Got it. Yes, thank you.
All right, thanks everyone. Well, we are 2 minutes over. So I want to take this time again to thank everyone. And as I mentioned, we're only limited to 3 perspectives. But if you have any other things that we didn't touch on that you want to capture, I see somebody's putting in references, go for it. That's great. There's also the section up here. There's a general notes section here. There's a couple other general notes sections. Actually, this should actually say part 2. That's a mistake on my part. And then just to remind everybody that if you didn't get a chance to attend the other sessions, the notes for those mini breakouts, you're going to find them. You scroll up here, you'll find them here under these Zoom breakout ID numbers.
You know, David,
yes, go ahead.
It seems to me we didn't spend much time talking about steps forward, next steps to take, and who is going to go work on the follow-up of the next version of the white paper and all this kind of stuff. I don't know if people have time to stick around for a few more minutes to talk about it, or whether we should take it offline.
Yeah, it's okay for me to stay a little longer.
I can stay longer as well. I just didn't want to pressure anyone, and maybe we can stop recording now. I'll just go ahead and do that.